design and manufacture, the fixture design and manufacture, the machine condition, including filtration, the gauges and technique used, the lubricant chemistry, condition and application, and the machine operator.
What was interesting about this particular investigation that we did is that the wear patterns on the cutting edges were very evident of being a chipping type of wear pattern. There's essentially 11 types of wear patterns that are fairly clear with fairly unique causes and cures. In this case, this is a classic type of wear pattern that you see on a cutting edge that was used with a chatter condition.
It was determined that adjustments in Protomatic's coolant chemistry and its filtration were needed to stabilize their high-speed machining operations. Gary Rodak explains.
When you're moving from low-speed or conventional type machining speeds to high speed, the metalworking fluid is much more critical. Flood rates have to be proper, cleanliness is critical, and so is concentration. At slow speeds, they are still very important and often overlooked because it's one of those messy chemical things and it's oily and so on, and people don't like to mess with that. It's very important for low-speed operations also, but especially for high speed. You need to have good aim for your fluid and you have to have very clean fluid. When you're dealing with a spindle that's working at 15,000 or 20,000 RPM, small sediment lodges in areas that actually destroy the internal workings of that spindle. You can wear out your pumps very quickly, so it's not the 20 micron particles that are easy to filter that cause the problem, it's the small 1 to 5 micron range that creates most of the problem.
As with any technology, high-speed machining offers an opportunity to learn new approaches to manufacturing. In Protomatic's case, the lessons learned were twofold.
One is a selection of the right type of equipment, and that goes coolant and tooling and tool holders. But also the other large element is the personal side, and is probably the most significant, is proper training on the personnel. Personnel have to have the right tools to understand what needs to be done next. We're moving into a territory that it is not intuitive. It is an area that you need tools to understand and to make corrections from feed, your speed, your RPM, and depth of cut, and those are critical in the decision-making process.
Helping manufacturers to refine their high-performance machining operations is the goal of Plymouth, Michigan-based Gossiger 3D. The facility develops and tests both high-speed and hard-milling machining systems, offering customers a full line of machine-related services along with the necessary technical support. High-speed and hard-milling operations are similar in technique, but their differences are distinct. Dale Mickelson elaborates.
The way we define high-speed machining to hard milling is high-speed machining is the pre-rough or the roughing of the material before heat treat. Or if it's an aluminum or if it's a material that doesn't get heat treated and you actually have a finished product, when you're done, there's no after process, then high-speed machining would use for the finishing. Basically, hard milling is where we put the accuracy and finish into the part after heat treat. Okay, so in that case, we're replacing, in some cases, EDM. We're replacing EDM trode and EDM wire, and also hand polishing or jig grinding.
Hard milling, like high-speed machining, can produce parts quickly, often with little or no post-machining work required. But companies are often skeptical about these claims.
We get into companies that actually can't believe we can make their part in 18 minutes when they're making it in 2 hours. We actually go in and it really takes the customer to understand by seeing. They have to see the process and see their parts being made in this process.
As with high-speed machining, hard milling requires looking at the machine tool, tooling, and software as integral components to achieve optimum results.
The base of the hard milling process is the machine. So there's certain machines we look at for doing this process, and they're rigid, accurate. The next part of the process basically is the holders. If they have conventional style holders or conventional style setups, then they try to go into hard milling. Basically, it gets pretty hard for them. And a lot of companies actually try hard milling that way and don't succeed at it and give up on it. We use a certain holder for the application, hard milling and high-speed machining. We're looking for holders that are rigid and terrific TIRs and actually have dampening effect, holders like that. The software that I would recommend are softwares that are basically made for hard milling and high-speed machining. We're looking for something that'll actually put out good finishes, have arc in and arc out ability so it flows into the material slowly and smoothly. The ability to basically put out a good finish is our biggest goal on that software.
The softwares most beneficial for hard milling and high-speed machining operations create tool paths using a technique called trochoidal.
Trochoidal is basically circular interpolating through a slot, and a slot would be basically a linear move straight through it. Trochoidal gives it the ability to actually profile cut through a slot. Slotting would actually push the material through. The end mill would actually be pushing the material and creating an extreme heat. And the end mills today for hard milling are actually made for profiling, not slotting. When trochoidal first came out, I tested it to see really how good it was to compare to slotting, if it was really a positive because of the extended cycle time it would create. And in the tests I found that I was actually 9 times more tool life by using trochoidal over slotting. So again, we look for softwares that have trochoidal built into it, and something where a software would actually only put trochoidal where it needed to, not for the whole part. Okay, so we don't want the extra tool path.
Another software feature that assists in optimizing the machining process is stock recognition.
As we go in with a large cutter and remove a lot of the material, we're looking for the next cutter, maybe another roughing cutter, to actually go in and recognize where the material's been removed and only do the work it needs to. So eliminating air cut, that's another thing we need in our softwares.
Hard milling can reduce time and improve quality, but it has its limitations.
Some of the limitations to hard milling are basically some of the materials we get into. If they're over 70 Rockwell, the cutter technology just isn't there in some cases. Basically the coating maybe won't hold up, and then it's not feasible to actually hard mill when your cutters, maybe you give 5 or 10 minutes of tool life in a material over 70 Rockwell. In some cases, length is an issue for us. If it's a straight wall and it's more than 10-to-1 length to diameter ratio, we generally don't want to work with that either. That's where EDM would actually come in and work for the customer.
When it is an appropriate manufacturing option, hard milling can save time, money, and improve quality.
There was a case study we did that basically these are examples of a lot of case studies that we do. The customer is doing the parts in 30 hours using conventional EDM and hand finishing and basic machining, prepping the part. And they would make the trode. They made actually 3 electrodes, and then they would polish the 3 electrodes so they didn't have any machining marks in it. Then they would EDM the part, and when the whole process got done, they would polish the part. And what we did is went in and actually made the part. It was S7 58 Rockwell. We made the part in 2.5 hours for the customer using hard milling.
When Metal Fab Incorporated, a job shop in Frederick, Maryland, began purchasing high-speed machining centers, the main attraction was production speed. With approximately 100 customers, Metal Fab's specialty is limited production of prototypes with a quick turnaround time. Don Swart explains.
What we found out was that so much of the work today is being sent overseas for production. And plain and simply, we can't compete in that market. So we decided to take on the prototype, quick turnaround type stuff. As I've put it sometimes, a lot of the companies are trying to find the new mousetrap. Everybody's out there, quickly give me 5 pieces. I need to go test it. I need to find out if this will work. If this works, this will sell. There's a big market for that.
Metal Fab's fabricating and finishing services are used in a variety of high-end communication technologies, such as cell phone towers. As a habit, Metal Fab typically switches out their machines every 5 years. So when the time came, they looked at high-speed machining centers.
I found everybody, they said they had high speed, and it was just higher RPM, but you really weren't gaining anything because they didn't have the accelerations and decelerations. And in a lot of cases, these improvements, so they would be higher RPM and a little bit faster feed rate, but you really couldn't do it. You were only gaining 10-15% in your production. And as we got into, what our customer needs are, I needed something that was going to improve at a much higher rate than that.
After determining that high-speed machines would meet their performance needs, Metal Fab found that they also required a significantly different approach to machining than conventional milling.
The main difference is depths of cuts and widths of cuts. You can't take the widths or the depths of cuts you used to, but you are machining so fast that the shallower depths of cuts or the less step overs you have, you're machining so fast that it makes up for it. We went from a 1/4 inch depth of cut to 125, but we're running 5 times as fast feed rate wise, 10 times as fast feed rate wise. So now you have, instead of cutting time in half, you cut time by 4, even though you're taking twice as many cuts.
Metal Fab also changed over all their tooling to take advantage of the high-speed machining centers.
We went from using standard end mills to millimeter end mills, because instead of jamming a 1/4 inch cutter into a corner to get a 125 radius, we're now rolling the corner like you would on the side of a part. You can actually go in and just mill right around the corner with basically a smaller end mill. So you get away from the chatter in your corners that way. Makes a lot smoother transition between one and the other. The deceleration rate as you're coming from a straight line into a radius is so, right now it's like I believe it's a 1/16 of an inch is where it actually starts to slow down before the transition, where before it might have been a 1/2 inch. So you're getting that extra at 450 inches a minute, or however fast you're machining, into that corner before you start in. As long as you roll a corner, you can keep the feed rate up. The feed rate, instead of trying to transition from a straight line to a radius, where before it would slow down a 1/2 inch before to go into a radius and it would ram into the corner, now it's actually rolling at 450 inches the whole way around the corner and back out. There's no deceleration rate because you have a smaller radius.
To eliminate some chatter and vibration issues, Metal Fab focused on the type of tool holders they were using.
The chatter and vibration we got around by going to solid holders, heat shrink holders. Basically, you heat a holder up, you drop an end mill in, and as it cools, it shrinks the end mill right into the holder. There's no more nuts. The holders are all balanced, which is a big part. That's an intricate part of the whole thing, is having balanced holders. You can't have a holder that's running out, or that automatically causes your chatter through harmonics. The chatter on the sides of a part wasn't a really big deal for us before or after we changed. The biggest part was in your corners, any corners you had in a part. That's where you end up running into problems, because the radius on the end mill is too close to the radius in the corner, and it basically sucks the end mill in. The other part was the tooling we used. We went to an end mill that was a real high density carbide, micro grain, and they are a heavy end mill, and they will absorb a lot of shock.
Metal Fab, on some prototypes, can boast an 8-hour turnaround time. However, because of the nature of high-speed machining, it does have its limitations.
High-speed machining doesn't work for all applications. As much as we would love to see it work, it does not work for everything. But if you weigh how many it doesn't work on compared to how many it does work on, you far exceed what you succeed on, and it becomes well worth the investment.
For those who are considering high-speed machining equipment, Don Swart offers this advice.
Don't skimp on the quality as far as, the machine you're thinking of purchasing, the tooling you're thinking of using, the programming system you're thinking of implementing. You have to go with the top of everything. There's no use having a $1 million piece of equipment and putting $30 tool holders in it. You need to have the best quality of everything. Find out what best fits your application, but then go after the really good stuff. It just stops headaches down the road.
Whether or not to invest in high-speed machining equipment is the same, it seems, as asking whether a company plans to stay competitive. While a high-speed machining center is a starting point, it's by no means complete unless it's integrated with appropriate tooling, software programming, and training. Additionally, by understanding your production needs and enlisting the assistance of suppliers, the greatest gains can be generated when making the transition to high-speed machining.